Good afternoon, everyone. Welcome to today's webinar on soil structure interaction for integral bridges. My name is Rohit Swaminathan. I'm working as a senior geotechnical engineer at MIDAS IT Poland. So today we'll be discussing about the soil structure interaction for integral bridges, starting with the initial theoretical aspects of soil structure interaction, the different approaches to soil structure interaction like the direct method and the substructure method. Then we'll be moving on to soil continuum modeling. What are the advantages of soil continuum modeling over the substructure method and the direct method? And finally, we'll be moving on to the integral bridges part, where we'll be modeling the structure in GTS NX. And I will also be discussing about the latest features and updates regarding the automation through the MIDAS API, which has the automated data transfer for interacting with Civil NX and GTS NX. So again, welcome to today's webinar on soil structure interaction, and we'll be focusing on the integral bridges part. Before we start, we would like to go through a theoretical background of why soil structure interaction is necessary and what are the different approaches towards the soil structure interaction. So we know that soil varies with space and depth. You have the spatial variability of soil in the X, Y, and Z directions. And it is necessary to consider the behavior of the soil in each directions with respect to the loads that is coming from the structure. In the sense, the different soil types have different deformations or different behavior, considering a linear behavior or non-linear behavior. And we also know that there are a lot of material models for soils that simulate the behavior of the soil under unloading and reloading conditions. So these vary with the type of soil, the loading conditions, and also the type of applications, like is it an excavation process, is it a direct loading, or is it a seismic event, etc. Then comes the question, how does the load transfer occur from structure to the soil? So we know that the load transfers from the superstructure to the, let's say in case of the bridge, the load transfers from the superstructure to the pier cap to the piles, pile to the soils in general case. So we consider the interface between the structure and the soil. In case of integral bridges, we also have another interface, which is the abutment and the bridge interface, where the lateral earth pressure of the soil acts. So this is another loading case that has to be considered in case of the integral bridges. So the soil structure interaction essentially studies or defines how the load transfer takes place with respect to the connections between the structure and the soil. The next question comes, what determines the behavior of the structure for a particular soil condition? So you have different type of soils like sand, you have clay, sandy clay, rocks, you have soils that liquefy. So as we have discussed earlier, depending upon the different soil types, you have different behavior and different loading conditions. And it is necessary to perform the soil structure interaction to understand, first of all, how the soil deforms not only below the structure, but also someplace nearby the structure. And during the loading, how does the spring constants or the stiffness of the soil get updated, and how we can use this in the later analysis case. So let us discuss about the different approaches to soil structure interaction. These can be broadly classified into two methods, the substructure method and the direct method. In the substructure method, you model the soil as springs. The soil behavior, in essence, is modeled with respect to the force deformation curves or the force displacement curves. For example, we have a PY curves, which give you the lateral deformations for lateral loads, and TZ curves, which provide the settlement for vertical loading. So these are in essence determined from certain criteria or certain constants, like for example from the modulus of subgrade reaction, that tells us how the soil behaves in essence. For example, for the modulus of subgrade reaction, you have the deformation with respect to a particular pressure. So in essence, the input is the soil behavior, and these can be used to model a soil for different type of structures like piles, abutments, rafts, etc. We'll be discussing about more about the different type of springs present in civil NX for modeling different type of soil behavior. Before that, I will also tell you about the direct method. So in the direct method, the soil and the structure are modeled together as a single entity, and the analysis is completed in one step. So this is the starting towards the continuum based method, where you are modeling the soil as a continuum and the structure is also modeled together. So we have different type of springs, for example, starting with linear springs. So here you have different models to simulate the spring constants or the force deformation curves for the soil. So you have the Winkler foundation model, Boussinesq model, Vesic method, etc. that can be used to simulate the force deformation curves for linear springs. So these are widely used for preliminary analysis and studies. Here the soil modulus remains constant throughout the load application process. So one of the disadvantages is that the stiffness of the spring remains the same in both tension and compression. And here, as I said, the stiffness remains constant, and hence it is like suitable for simulating small strain behavior. And then we have multilinear springs or nonlinear springs. So multilinear springs are piecewise linear springs, and they have different values at different settlements, different displacements, different stiffness values at different settlements. So you do not have a completely linear curve, you have a piecewise linear curve that simulates a nonlinear kind of behavior. So again, you have different approaches to simulate the multilinear spring behavior. You have the Lahan theory, Rees and Matlock, Bowles, Vesic, etc., which fall under the empirical approach. And you do have the closed form elasticity methods, wherein these are simulated for each soil layer depth. For example, for the first layer, you have a particular form of force deformation curve. For the second layer, another form of force deformation with respect to the changing soil properties. So the closed form elasticity consists of different methods like Boussinesq, Paulus and Davis, Randolph, etc. So these are used to simulate the multilinear spring behavior. Yeah, so we have seen the two approaches towards modeling the soil structure interaction. The first one is the substructure method, and the next is the direct method. So the continuation of the direct method is a soil continuum method, where you will be modeling the soil with respect to 2D and 3D finite elements that simulate the stress strain relationships upon loading. So what are the advantages of the modeling soil as continuum? So the first advantage is that the plastic nature of the soil is considered. You consider the different, let's say, the unloading and reloading behavior of the soil. For example, you have different soil models that simulate the behavior of soil in different ways. For example, more Coulomb model, modified cam clay, soft soil, then you have UBC sand for liquefaction. So all these effects cannot be taken into account when the model is when the soil is modeled as springs, and can only be taken into account when the soil is modeled as a continuous medium. The pile group effect is can be considered. For example, when you have a pile group with pile raft foundation, wherein you have the pile raft interaction, raft soil interaction, soil pile interaction, and the pile interaction, these group defects can be considered when the entire model is modeled as a continuum. Another interesting advantage is that the varying strata can be modeled, so that the change in the in situ stresses can be incorporated within the model. So that is something that cannot be taken care of while modeling the soil as springs. The time-dependent properties like shrinkage and creep can be incorporated. And also this allows for us to check for safety and stability of the buildings directly in the geotechnical analysis tool. For example, you can bring the entire model from civil to GTS NX, and you can model the surrounding ground. You can do a liquefaction analysis. You can model the water table, seepage. You can model excavations near the structures, and run a different type of analysis like construction stage analysis or dynamic analysis, and you can check for the stability of the structure. And finally, it allows for the optimization of the design that we'll be discussing in the upcoming slides. How the updation of the spring stiffness in the model allows for the optimization of the design. Now, what are the advantages when it comes to the MIDAS program? So all this we'll be seeing in the upcoming slides. Brief overview here. So as I said, the interface, the tension cutoff, etc., can be incorporated, and there is efficient data transfer from one software to another because all the softwares are integrated in the same platform. And as I said, there is like the transfer of the spring stiffness and the force displacement curves between the softwares. And for structures such as critical structures such as integral bridges, this plays a very important and key role, because the integral bridge is a structure where you have like two places where the soil comes in contact with the structure. So you have the pile soil interaction, you have the abutment soil interaction. So both of these have to be considered. And finally, there is significant reduction in modeling time because the structure is modeled in a structure modeling tool, and it is entirely brought into the geotechnical analysis tool without any loss in data. This saves a lot of time with respect to modeling and analysis. Now let us talk about the interaction between MIDAS GTS NX and MIDAS Civil NX. So we know that the bridge models will be created in Civil NX. The entire modeling of the structure will be done along with the load case definitions, the loading, the different load combinations, and the analysis with respect to the different load combinations will be run Civil NX. And then we'll be transferring the model to GTS NX to model the soil as a continuum. So this is a brief overview of the integration architecture. So once the model is created in Civil and the analysis has been run, two of the files are transferred or exported to GTS NX. So basically we have an MXT file which contains the data of the geometry, the element properties, the material properties, all the data related to the model are embedded within the MXT file. Then comes the nodal results file. So in the nodal results, you have the reactions which are developed with respect to the different load combinations that you have assigned, and the reactions that are developed after the analysis has been run for the different load cases. So these two files will be exported from Civil, and these are imported into GTS NX, which is shown by the first processing gate, wherein the files, MXT file and the nodal results files are imported into GTS NX. In the second processing gate, you have the modeling of the soil continuum. So you create the geometry. So as we said, you can define different layers of the soil. You can define a particular terrain. You can model the stratigraphy of your soil, any nearby excavations. You can model the water table, etc. And finally, the final output will consist of one single entity comprising of the structure and the connected soil as a continuum with all the geotechnical as well as the hydraulic properties. So talking about the interaction between Civil and GTS NX, you can either just within GTS NX itself, you can just add the loads and obtain the deformations and settlements and other stresses, etc. This can be done in 2D and 3D as well. Other than that, you can study the interaction of the structures which are imported from Civil NX to GTS NX. Once the analysis is completed, you can directly view the deformations and displacements. And also you can study the interaction of these structures on nearby excavations and vice versa. And a noteworthy point is that the modeling time is considerably reduced in this case when you're doing the direct method. So as we had discussed, the direct method comprises of modeling the entire structure and soil as a single entity. Since Civil NX is particularly tailored for structural modeling, you have the model already prepared in Civil NX, and you are transferring the entire model along with the reactions from your different load cases into GTS NX to model the ground. So you have two separate platforms which are particularly designed for structural modeling as well as geotechnical modeling, and you are integrating both of them. This reduces the modeling and analysis time considerably. So the general idea of or the general methodology when coming to the initial soil structure interaction problem is, uh, as we had seen earlier, you import the MXT file along with the reactions into GTS NX, and you model the ground along with the other geotechnical conditions, and the force displacement curves after the analysis has been run in GTS NX is taken back to civil. So this is an iterative process. So one full iteration consists of the transfer of loads and springs between the geotechnical and the structural engineers. So in order for the design optimization that we had talked about earlier, it is necessary that the results, for example, the displacement results in the civil software as well as GTS NX converge at a certain point, and this usually takes around 4 to 5 iterations. In the upcoming slides, we will also be talking about how the manual iterations have been now automated using the MIDAS API. Yeah. So coming to integral bridges, we know that integral bridges are structures where the bridge deck and the supporting abutments and piers are constructed monolithically, and there are no expansion joints or bearings present. Rather, the forces are transmitted directly to the bridge abutments. So this makes integral bridges unique in the sense that the forces are directly transmitted to the abutments, unlike the conventional bridges. Now, the different types of load cases that come under the integral bridges are the self-weight, dead loads in the form of the loads from the road surface, the lateral earth pressure, loads from the wet concrete, etc. Live loads, which include the wind load, the pedestrian load, temperature loads include the expansion, the contraction due to the temperature changes, pre-tensioning, and the moving load analysis. For the simplicity of this particular analysis case, and due to the existing time constraints, we'll be only focusing on the static live loads that will include the self-weight and the dead loads in this particular analysis case. Now coming to the springs part, so we know that there are different type of springs that you can use, as we have seen earlier, like linear, multilinear, non-linear springs. When we talk about the integral bridges, we know that there are two portions where the soil comes in contact with the structure. So the first case is the abutments. So we need to provide the springs near the abutments. So we need the abutment springs. And second is the piles, where the pile comes in contact with the soil. So in this case, also we need to provide the springs for the connection. In MIDAS Civil, there is an integral bridge function using which the spring stiffness values can be automatically calculated using the Berry-Lani calculations. And in the case of abutment springs, we can provide the input with respect to the dimensions of the abutment and the properties of the fill, that is the void ratio, specific gravity, and the cyclic ratio. And in case of pile springs, the input parameters are the pile diameter, the unit weight of the soil, the earth pressure coefficient, subgrade modulus, and the modulus of friction, the angle of internal friction. So with these parameters as inputs for the abutments, the springs generated are compression only lateral springs, since these are acting in the lateral direction, and these are acting as the lateral earth pressure on the abutments. And in case of piles, the linear elastic springs are developed. Yeah. So now let us start with the modeling of our integral bridge. We are using an existing model that we had created, which consists of the deck, the abutments, and the piles. So you can see that we are considering only one static load case, which comprises of the self weight, the element beam loads, which we had, as we had described earlier, consists of the dead loads acting on the deck, consisting of the wet concrete load or the other kinds of loads that we had seen earlier, and the earth pressure loads, which are acting in the horizontal direction, that is on the abutments. So these are the different types of loads that we have considered in case of this particular analysis. So as we had discussed in the integration architecture, the first step is to export the two files. The first one is the MXT file, which consists of the geometrical details of the model and the material properties of the different elements, and the element properties like what type of elements are being used in the model, such as plate elements, beam elements, etc. So we can export the first MXT file. So this will be saved here. We can save it as test01. Yeah, so you can see the MXT file text editor. So all the input informations are stored as a text format. Now we can run the analysis with the respective load cases. Yeah, so once the analysis is complete, we will export the respective reactions as well. So these are exported as nodal results. So you have an option to either choose reactions or displacements to represent the force deformations for your structure. So in this case, I'm going with the reactions. Click on add and OK. So I'll save this as well. Yeah. So the reaction results from the analysis for the respective load cases have been saved. Yeah, so let's start modeling in GTS NX as well. So first we will open a new file, and we can directly import the MXT file here, which contains the geometry of the structure along with the material and element properties. So I can choose the MXT file that I have imported. I have exported from Civil NX. So here you can see the warning that the property of the point spring has been changed because multilinear is not supported. So it does not matter as we are not modeling any springs in GTS NX. All our connections will be modeled with respect to the soil continuum method, and all the boundary conditions, everything will be defined with respect in GTS NX. So this warning is okay. So the first thing I can do is I need to delete the point springs. So if I go to analysis and the load cases, I do not need the loads as well, because we will be importing the reactions that are developed because of the different load cases in the model. So we will delete the loads. Next is to delete the boundary conditions that have been imported. So all the boundary conditions as well we will be defining in GTS NX. And if you see in the model, these are the point springs. So the point springs are basically, as we had said earlier, the connections that were created at points or locations which are in contact with the soil. So earlier we had defined the abutment springs near the abutments, on the nodes on the abutments, and elastic springs on the piles. So these have been the abutment springs here have been converted to a point spring. So all these springs we'll be deleting, which are not needed. Instead, we'll be connecting them to the soil continuum. Okay, so the springs have been deleted. Now we have the skeleton of our integral bridge, and we need to next define the soil continuum model. So that will comprise of the ground and the fill as well. Yeah, so let us define the ground properties or define the ground geometry first. I can go to the work plane and adjust it according to my preferences. And I will also define the initial ground boundary. Okay. So I can use the geometry creation tool options. With respect to the users, each user has their own a way of creating the geometry. So in this case, I am initially using the 2D tool, 2D surface tool, and then I'll be extruding the 2D surface to form a 3D geometry. So this particular surface I'll be moving here to the bottom of my abutment. Yeah. And I can extrude this portion using the extrude command in the vertical direction to a depth of minus 20 meters. I'm assuming a uniform soil layer here. Yeah. So the ground layer has been modeled, and we'll be considering fixed supports at the bottom and horizontally fixed supports on the sides, vertical sides of our ground, so that there are no horizontal movements. The horizontal movements are restricted on the sides. Okay, so next step is to model the geometry for the fill material, which will be coming on back of the abutments. So in order to provide that, we also need to extend the geometry. So I'll use the extrude command again, select the direction. I'll put a length of 5 meters for each of the fills. Okay. Now I need to extend the fill to the top of the abutment. I'll use the 2 points vector command here to get the exact height. Similarly on the other side as well. You can use the 2-point vector. Yeah. So now you have the geometry for each of the ground as well as the fill on both the sides. I can use certain tools to create a more uniform geometry. So the first is the combine or diffuse tool. So I can make the geometry one. The next thing I can do is use the auto connect tool to connect all the geometries so that the shared faces are created when I am meshing the model. Yeah, so the next step in the geometry creation is to ensure that the nodes within the piles and the nodes within the abutments get connected to the ground and the fill mesh during the meshing process. So this has to be ensured. So in order to ensure this, we need to follow a certain procedure. So initially we'll create points at the nodal locations. So first of all, I'll activate the abutments and the pile alone. So the north piles and the south piles, and I will switch off the rest of the geometry. So here I can only see the abutments and the piles where the nodes connecting to the soil is present. And now I will convert each of the nodes into points, geometrical points, which will allow me to connect each of the nodes to the meshes later on. So I use the point option, convert node, and I just select all the nodes here on the abutments and the piles and click on OK. Yeah, so here you can see the nodes have been created at each point. The points, geometrical points have been created at each of the nodes present on the abutments and the piles. So now this will facilitate the creation or the connection of the nodes onto the 3D soil meshes. Okay, so first of all, let us also connect the nodes on the abutments to the fill. So I can switch on the geometry. Okay, I will first use the imprint command. So here I'll choose for the imprint of the point. I can select the target object, select tool as all the nodes present here, and click on the direction of shortest path line. Click on apply. So those have been imprinted. Similarly, choose the second fill geometry as well and do the same procedure. Okay, so now the points have been imprinted on the geometry. So this will ensure that while performing the meshing operations, all the nodes are present. All the nodes for the 3D meshes are present where the nodes for the abutments have been imported. So the connections will be maintained. Now, even if you switch off the original geometry points, you can see that the points are already are existing on the 3D geometry. That means the imprint has worked. Okay, now let us go back to our model without the geometry. Yeah. So the next step after creating the geometry is to define the material properties. Yeah. Coming to the material properties part, we can go to mesh and click on material. So here you can see that already some of the materials have been imported when we had imported the MXT file. So these are for the different elements present here. And now we need to define the material properties for the ground as well as the fill. Here you can use the isotropic option and assign any particular soil model with respect to the different types of soil properties that is present. And you can choose a more column model, and you can provide, let's say, the nonlinear parameters with respect to the cohesion, friction angle, etc. Now, there is also another option wherein you can directly import the material property and the element property from another file. So let's say I can choose a particular file here, and I have the ground and the fill properties already defined earlier. So I can use the import feature, which is a very good feature in GTS NX, using which you can import the material properties from other files. So in essence, you do not need to define the material properties each time. You can import it from another file in which already it has been defined. So if you see now, the ground material property and the fill material property have been defined. And it consists of the elastic modulus, the unit weight, cohesion, and porous nonlinear parameters all have been defined here. Okay, so similarly for the fill material as well. Now, coming to the meshing part. So let us again switch on the geometry. Okay, and we'll switch on the points as well. Okay, so switch on 3D, and we'll assign a size of 1.5 meters. I'll choose the hybrid mesh and change the name to ground to assign the ground material property. And here, since I need the connection between the piles and the ground, I'll also select the interior points. So the interior points connecting the ground with the piles will be selected. Click on OK, and click on the object and click on apply. So now we can see that the ground mesh has been created. Now moving on to the fill mesh. So again, I can use the same mesh size. I'll just change the material property, change the naming. I can select both of them together and just click on OK. Yeah, so since here we have already defined the connection between the elements, so you can see that the connection has been maintained. Yeah. Now, so the fill meshes as well as the ground meshes have been defined. I can switch off the geometry now. So the next step is to define the boundary as well as the loading condition. So in this case, I'm defining only the self weight, since the other loading conditions will be based on the reactions that I import from civil. So I can do it now. Go to import, nodal results, and we have saved it here. And these will be the nodal results for our analysis. Okay. Can switch off the view. And self weight I'll be defining here. So I can define the self weight of the model. Click on OK. And next I can define the boundary conditions. So can go to constraints, click on auto, and I can define the model boundary. So the auto boundary constraints defines the model boundary in such a way that, as we had said earlier, the vertical sides are fixed in the horizontal directions, and they can move freely in the vertical directions. So they are essentially roller supports. and the bottom is completely fixed. So the vertical sides allow roller supports to allow for the deformation in the vertical direction, and the bottom of the model is completely fixed. Now we can proceed to defining the type of analysis. So here you can add any other loading criteria or any other boundary conditions with respect to your discretion. And now we can move on to defining the construction stage analysis if we want, or directly define a nonlinear static analysis. Yeah, so let us define the nonlinear static analysis. So I click on the analysis case, add a new analysis. I can change the analysis type to nonlinear static, and I can assign the model boundary and both the loading cases. Go to analysis control and click on the in situ analysis for considering the in situ soil stresses. I can clear the in situ displacements which are not required, and change the number of iterations, increments in the iterations, and adjust the convergence criteria for a smooth analysis as well. Okay. Now let us run the analysis case that has been defined. Yeah. So once the analysis case has been run, we will be exploring the results within the model for the given analysis case. And the results from this particular analysis, that is the updated spring constants with respect to the force versus displacement curves, can be taken back to civil for performing the design optimization. So yeah, here we can see about 80% of the analysis is completed. So similarly, you can also add the construction stage analysis, where the initial soil is considered, then you are activating the piles, then the abutments, decks, and fill. So the stage construction can also be considered, and the results can be taken back to civil as we have discussed earlier. Yeah. So once the analysis is completed, yeah, we can see the results for the piles. So let us go again to the abutments and pile foundations. We can simply switch off the fill and the ground meshes. Let us look at the results for the axial forces in the piles. Yeah, so these are the axial forces developed. So throughout the load increment. So then the shear force variation in the piles and the bending moments. So these are for the bending moment in the y direction. So in the z direction, you can see in the piles as well. Okay. Yeah. So once the analysis is completed, we can export the results back to Civil NX. So I can click on export and export nodal results. So I can choose the load sets by force option here. So it will consider the load combination or load case that we have considered, and the analysis set case. And you can choose the force displacement type, and which result combination we will choose all. That means it contains all forces and moments in all directions, and we can save this as another text file. So this will be saved as GTS to civil. Right. Okay. So now these will be the updated spring stiffness values for the piles as well as the abutment springs. Now we can go back to civil, and here what we have to do is we have to delete the already existing force deformation curves. So I can delete the existing force deformation curves and import the nodal results. So GTS to civil. So it has been completed. So you can see in the force deformation functions, the new force deformation curves have been imported. Right. So again, so this is the iterative procedure. So we run the analysis once again. with the updated springs. And here again the reactions change, and the reactions are again taken back to GTS NX, and the analysis is run on an iteration basis. So depending upon the convergence criteria that you define, so the convergence criteria can be with respect to a certain force like a bending moment or a shear force, or it can be with respect to the settlement or the lateral deformation that you're observing at a certain point. So depending upon the convergence criteria, we can define the number of iterations for a particular analysis, and the iteration with respect to the calculation of the nodal results, the export of the nodal results, and export of the reactions into GTS, and running the analysis in GTS and taking back the updated spring stiffness values into civil. So the iterative procedure has to be done till the convergence criteria has been met. So this is the iterative soil structure interaction procedure that is integrated fully with Civil NX and GTS NX. This process of the iterative soil structure interaction between the model in the structural model in Civil as well as the geotechnical model in GTS NX has now been automated using the NX interact function, which allows for the automated data transfer between the two softwares. I'll be showcasing that now. So following the same procedure, let us go back to GTS NX, and we have the NX Interact tool here. And also we have in Civil NX, the NX Interact tool is available in the apps, in the API settings. So what I can do is I can move the points here so that it will be easier for us to compare the two. So let us go to the API settings. We copy the base URL here, copy the MAPI key. Okay, so it is showing connected in the API settings. So we connect it here in GTS NX as well. Okay, so the number of iterations here, the number of iterations refers to the iterations that we have done in earlier in GTS NX and Civil NX. So the process of taking back the nodal results from GTS to Civil constitutes one iteration. So we'll have the iterations, let's say 4 iterations, and you can save the analysis, all the results for all the analysis. You can save the results for all the iterations as well, and click on the analysis phase. So it says connected, and it is saving the files now, and it is first running the analysis in Civil or Gen, and you can follow the steps in the NX Interact screen. So the reactions are being imported, and now the analysis is being run in GTS NX. So you can see that the entire process of importing the results from Civil to GTS NX and running the analysis in GTS NX and then exporting the results back to Civil NX has now been automated. Yeah. So this analysis moves on. Yeah, so now the analysis has been completed with respect to the 4 iterations. I have fast forwarded the analysis here. And for each of the iterations, you can see that the separate GTS NX file has been created. Similarly, a separate Civil NX file will also be created for each iteration. So you can check the results. Yeah. This is the NX interact function within GTS NX, and it has been integrated with Civil NX and Gen NX, which is the building design software for general structures, which allows for the automated data transfer between the MIDAS family of softwares. So an example of the results from the SSI iteration test is shown here. So you can see the 4 iterations as I had shown earlier. So for each of the iterations, the interact function has created a separate SSI file both in GTS NX and Civil NX. So these are the results extracted from the bending moments generated in the pile foundations. So you can see the convergence of the bending moments around the SSI 3 and SSI 4. So this is the convergence criteria that has been mentioned during the analysis procedure. So the convergence criteria can be anything starting from, let's say, the bending moment of the shear force, or the settlement of the pile, or the lateral displacement. With respect to the convergence criteria, here the number of iterations at 4 has resulted in some form of the convergence, but you can also like do 2 or 3 more iterations to confirm whether the convergence has been achieved. Yes, so this is the final part of today's presentation, which deals with the NX interact function that I had shown earlier. As I said, it deals with the fully automated data transfer between the two platforms, which allows for the automated soil structure interaction analysis. And here you have the NX interact functions. With respect to the number of iterations that you give, you can run the analysis. So the major advantage, as we said, with respect to the with respect to soil structure interaction, is that the integration between the platforms in MIDAS is extremely good, so that the process of taking the results for a structural engineer to a geotechnical engineer and back, which forms the basis for the soil structure interaction process, is automated and made very easier. So the initial process, which was manual and a tedious and tiresome, which used to take the time from the structural engineer to initially define springs, then run the analysis and give the results back to the geotechnical engineer. So the geotechnical engineer has to run the analysis and share the results with the updated spring stiffness back to structural engineer. And again, the iteration process has to be continued with the communication in between. So this process has been now entirely automated with the API integration. So that's all from my side for today's presentation. So if there are any doubts, I would be happy to answer them all. So thank you.